Hello, everyone. Welcome back to the Qiskit live seminar series. I am Maria Violaris, and I am your host for today's talk by Yoshifumi Nakata on decoding random codes. I work part-time with the Qiskit community team, mostly making videos for the Qiskit YouTube channel and other quantum content alongside my PhD at the University of Oxford. Now, while we wait a few minutes for everyone to arrive, I would love to know where you are all joining us from today. So please use the live YouTube chat to tell us where you're joining from. The live chat will be open throughout the seminar, so please feel free to drop in questions and comments there for me and our guest speaker at any time. I am currently in Bristol in the UK, where it is 5 p.m. in the afternoon, and we have people joining from Portland, Oregon. We have from Oxford, England. Hi, Zengrong, who put that one. Chicago, Poland, Washington D.C., Costa Rica, Leeds, San Diego. Wow, we've got lots of different places today. Dominican Republic. Oh, great. Please keep the locations coming. It'll be great to see where you're all joining from, and thanks for tuning in from wherever you are in the world in different times. We have Brazil as well. It's great. Please keep those coming while I introduce today's speaker. So hello to anyone that's just joined us in the last few minutes. I'm your host, Maria Violaris from the Qiskit community team and University of Oxford. This seminar happens live every week at 12 p.m. Eastern Time. All of the episodes are recorded, and you can find them on the Qiskit YouTube channel, which I encourage you to subscribe to if you haven't already. But you can only ask your questions in the comments if you join us live. So it's great if you're joining us live today. And I hope that you will all enjoy the seminar. So I'm here today with today's speaker, Yoshifumi Nakata, who will speak about his work on decoding quantum random codes. Yoshifumi is a research associate professor at the Yukawa Institute for Theoretical Physics at Kyoto University in Japan. He works on theoretical quantum information science and has research interests in both foundations and applications of quantum technologies. Welcome, Yoshifumi. Thanks for giving the talk today.
Yeah, thank you very much for inviting.
Yeah, where are you tuning in from today?
I'm now sitting in the seminar room in the Kyoto University, so I'm now in Kyoto, Japan.
Cool, great. Yeah, thanks for joining us in the early morning of Japan. Yeah, and it's always great to see researchers with interests at the intersection of foundations and applications of quantum things. It's a great combination, I think. So yeah, whenever you're ready, please feel free to put the slides up, and over to you.
Okay, so thank you very much for the introduction. I'm Maria, and thanks everybody for coming to this seminar. So today, I would like to talk about quantum random codes, especially from the viewpoint of how to decode them. So this is the outline of this talk. I would like to start with the brief introduction about quantum random codes. Well, actually, quantum random codes are a kind of standard technique in quantum Shannon theory, but I'm not so sure if everybody is familiar with quantum random codes. So in the introduction, I would like to explain the basic idea and basic facts about quantum random codes. I hope I can motivate you why we should care about quantum random codes in the introduction. And then I would like to talk about our recent papers I have written up with my collaborators. And the first paper is about random stabilizer code, and we are going to talk about their efficient decoder. And in the third part of my talk, I will propose a new decoder based on the complementary principle. And actually, we can decode any kind of quantum error correcting code by using this decoder. And the second and the third, I mean, these two results are not directly related to each other, but both are concerned with how to decode quantum random calls. So in the end of the talk, I hope you get some idea about, how to decode these random calls. Okay, so with this, let's start the introduction. So here, again, I would like to explain quantum random calls and try to motivate you about the quantum random calls. Good. So let me start with a brief recap about the quantum error correction. What everybody should know about quantum error correction because it's so important in quantum information science. But quantum error correction is a method to effectively cancel quantum noise in quantum systems. So here we have a very simple diagram. So we, for example, want to encode some quantum information or unknown quantum state psi into a quantum system. But of course, quantum systems are typically very noisy. So if we don't do anything, as time goes, the system gets noisy and eventually we lose all the information about the initial state. So this is a very common situation in quantum systems. And we can avoid this situation if we use a quantum error correction technique. So the idea is to use an encoding operation before the system gets noisy. And after the system gets noisy, we just perform decoding operation. And the goal is to construct encoding and decoding operations such that as a total of three time evolution, we want to achieve the identity map so that if the initial state is psi, then the final state is also psi. So this is a very brief overview of the quantum error correction. And as I said, this is really important in quantum information science because without performing quantum error correction, we can never achieve a large-scale quantum information processing, such as quantum computation or quantum computation, etc., etc. So really, quantum error correction is a key of in quantum information processing. And also, there is an increasing interest in quantum error correction in theoretical physics as well. So, for example, people in theoretical physics are exploring quantum error correction to understand very complicated physics, such as quantum gravity, quantum chaos, and also new quantum phases. So, if we use some technique from quantum error correction, we could better understand these things. And for this reason, many physicists are interested in quantum error correction these days. So, from many different perspectives, quantum error correction is important. And there are many different quantum error correcting codes. And one of the most common quantum error correcting code is a class of stabilizer code. For example, surface code like Shor's 9-qubit code, concatenated code as well, and also LDPC codes. All of these things are a type of stabilizer codes. And the main reason why we usually focus on stabilizer codes is they have good properties. So essentially, stabilizer codes can be constructed by combining two classical codes with good properties. So when we study stabilizer code, we can use lots of techniques from the classical coding theory. So this is a good property that makes the analysis easy to understand stabilizer code. And also in the stabilizer code, the decoding task is a kind of straightforward. I'm not saying decoding is easy or decoding is efficient, but the idea is kind of straightforward because in the stabilizer code, we have lots of stabilizers. So we just perform some syndrome measurement onto the noisy system. And from the measurement outcome, it's a classical information. We just perform some classical decoding. And by combining these classical decoding, we can construct a decoder for stabilizer code. So essentially, decoding task falls to the classical decoding for stabilizer code. And this is also a good feature of stabilizer code, I think. And of course, if you use a special type of stabilizer code, we can achieve fault-tolerant computation. That is another good point of stabilizer code. And for these reasons, we usually consider a stabilizer code in quantum information. But there's certainly another class of quantum error correcting code. And today we want to discuss about a class of random codes. So actually there's an overlap between stabilizer code and random codes, but essentially random codes are kind of different from stabilizer code. So we are going to talk about this. But let me now explain what is the quantum random code. So yeah, in the random quantum random code, we are going to use a random unitary for encoding quantum information. So here again, we have a simple diagram of quantum error correction, and we just use a random unitary for encoding operation. And here I just said random unitary, but we use a different type of random unitary, and different type of random unitary defines a different quantum random code. And the typical choice of a random unitary is a Haar random unitary. And I don't know if you have heard of this word, but this is a very simple random unitary where we just pick up one unitary from the big unitary group. So assume that you have an n qubit system, and then the unitary forms a unitary group acting on n qubits, right? So it's a big group, but we just uniformly we just choose one unitary uniformly at random, and that is called a Haar random unitary. And if we use a Haar random unitary, actually we can achieve a very high performance quantum error correcting code. And that is sometimes called a free random code. So in this talk, when I say a free random code, I refer to the quantum random codes generated by a Haar random unitary. Although this is a typical choice of a random unitary, we can use different types of random unitaries. For example, instead of a Haar random unitary, we can use a random Clifford unitary, which is a substantially smaller subclass of unitary. Or we could use a random circuit to define another type of random code. So depending on what random unitary we are going to use, we have many different types of random codes. And in the last line, I just wrote quantum chaotic dynamics. Because these days, some people, well, actually including me, are exploring to use a quantum chaotic dynamics, I mean the Hamiltonian dynamics in quantum system, quantum many-body chaotic system, to encode quantum information. And actually that works very well. So if we use quantum chaos, we can actually achieve a good quantum error correcting code as well. So this is a kind of brief introduction about the quantum random codes. So the point is, depending on what random unitary we are going to use, we have different random codes. And if this is your first time to hear about quantum random codes, probably you'd wonder, why do we use random unitary for encoding quantum information? Why do we use such strange things? The reason for this is quite obvious. Actually, quantum random codes typically have a very high performance of quantum error correction, especially in terms of the encoding rate. So encoding rate is just a ratio between the number of logical qubits and the number of physical qubits. So encoding rate is the number of logical qubit per physical qubit. Okay, so we define the encoding rate in this way. And quantum random codes have a very high encoding rate. But encoding rate is actually kind of trade-off to the error tolerance. So if we try to encode too much logical information into a restricted number of physical qubits, then that quantum error correcting code cannot be tolerant against any noise. So there should be some trade-off relation between the encoding rate and error tolerance. So to explain how good quantum random codes are in terms of encoding rate, so let me here assume some concrete noise model. So in this slide, I would like to assume an independent depolarizing noise, meaning that each physical qubit is exposed to the single qubit depolarizing noise given by this. And if we assume this error noise, and by using some techniques in quantum Shannon theory, we can obtain some trade-off relation between the general trade-off relation between the encoding rate vertical axis and the depolarizing parameter in the horizontal axis. So here you can see the blue dashed line, and this is an upper bound of the achievable encoding rate. So this means that this black region, above the upper bound, no quantum error correcting code can achieve this region. Okay, so this is a very general theory about the encoding rate and error tolerance against the independent depolarizing noise. And if we draw the encoding rate achieved by the quantum random calls, it's something like this. So here we have a red line. This is a rate achievable by free random calls, and this is known as the hashing bound. As you can see, this red line is a kind of close to the upper bound, and sometimes people conjecture that this hashing bound might be the optimal line that we can achieve by the best possible quantum error correcting calls. So from this figure, you can see that quantum random calls have a very high encoding rate. And just to emphasize how good this is, let me give you some kind of side note. So for example, if we use a surface code, we can of course correct independent depolarizing noise to some extent. But the drawback of surface code is its encoding rate is not so high, in the sense that if n goes to infinite, the encoding rate of the surface code should tend to 0. So if we draw the trade of encoding rate and the depolarizing parameter for the surface code, it's something like this line. So of course, surface code can be tolerant against depolarizing noise to some point. I don't know the exact number, but it can be tolerant. But the encoding rate is always 0 in the asymptotic limit. So compared to this surface code, this quantum random code is pretty good. So this is a reason why people, especially in quantum Shannon theory, care about random calls. It has a high encoding rate, and sometimes it is best possible error correcting code that we can achieve. But of course, there are several caveats about the random calls, and that is what we want to discuss in this talk.
Can I jump in with a question that came up?
Sure.
Was can MNISC or Q dataset be used as standards?
Sorry, can you say it again?
Are you familiar with I'm not sure what they are myself, but can MNISC or Q dataset be used as standards? Is the question.
MNISC Q. Sorry, I have never heard of that word.
Okay, well, maybe if the person that asked the question would like to clarify in the comments, feel free. But yeah, otherwise we can carry on.
Yeah, I'm sorry. Yeah, I really it's my first time to hear that word. So yeah, if you want to know more, please just describe it. Yeah, meanwhile, yeah, I can just continue my my talk, I guess. Okay, so we were just talking about some caveat about the quantum random calls, and caveat is about the encoding and decoding complexity. So the real question we are going to ask in this talk is, can we efficiently encode and decode random calls? So this is a very important question when we are interested in quantum random calls. And let me explain just one by one. So first of all, what is encoding complexity of quantum random calls? Sometimes people say quantum random calls are pretty inefficient because people usually imagine to use the Hall random unitary for encoding these quantum random calls. And if we use the Hall random unitary, of course, this is extremely inefficient because if we want to implement a Hall random unitary by quantum circuit, we have to use exponentially many gates in terms of the number of qubits. So we cannot efficiently use the Hall random unitary. And that's why people sometimes say quantum random calls are inefficient. However, as I emphasized in a few slides back, we can use different random unitaries. And in fact, less random unitaries, less random than the Hall random unitary, typically have the same performance as free random calls. So instead of using a Hall random unitary, we can use a less random unitary And we can show that these random unitaries can be implemented by quantum circuit with linear depth in terms of the number of qubits, or sometimes less a shallower quantum circuit is sufficient for achieving random unitary. So if we use these random unitaries, we can actually encode quantum random code efficiently. So there's no problem about encoding complexity. On the other hand, decoding complexity is highly non-trivial, and it is in general hard because the classical counterpart of quantum random code, which is just called classical random code, is the decoding task for the classical random code is known as a NP-hard problem. So there is no hope to decode all quantum random codes efficiently. So this is an established result. So the real question is, are there any circumstances under which efficient decoding of random codes is possible? So this is a question I want to ask, or I have been working on in the last couple of years. And
Can I
today,
just jump in with just a clarificatory question about encoding? The question is, what do you mean exactly by encoding with a random unitary, a classical string of bits encoded in a quantum state? That's the
no, we just prepare some logical degree of freedom. So it's an unknown quantum state. And basically, we are going to apply random unitary to the yeah, I will show you, but we have an unknown quantum state and we have lots of ancillary systems, and we just apply random unitary. And by doing so, we can actually encode this unknown quantum state.
Mm-hmm.
Does this make sense? I will give you some figure very soon, actually.
Yeah, thank you. Thanks.
Yeah,
Please.
great. Okay, so this is a question we are going to ask. And in this talk, I want to share two results that we have obtained actually last year. So in the first result, we considered the random stabilizer code. So random stabilizer code is a kind of class of stabilizer code as well as a class of random codes. So it's sitting in an overlap between stabilizer code and random codes. And in this case, we show that both encoding and decoding are efficient. And also these random stabilizer codes are as good as free random code. So this is kind of great because both are efficient and we can actually use these random stabilizer code. So we believe that they may have a practical application. And in the second part of my talk, I would like to focus on the non-stabilizer random codes. So just general random codes. And in this case, decoding is really non-trivial because these codes are not stabilizer codes anymore. So there's no idea of stabilizers. There's no syndrome measurement. So when we want to decode general random codes, we have to start from scratch. So decoding is really non-trivial. And in the second result, we are going to provide a new construction of a decoder based on the complementarity principle. It's a very fancy word. But actually, the second result is kind of on the way because we haven't succeeded to talk about the decoding complexity of our new decoder. So although we are interested in efficient decoding, about the general random code, we can just provide how to decode it, and we never talk about the efficiency. But this is a kind of good step toward the further progress. So in the second part, I just talk about how to construct a decoder. So these are the kind of results that we are going to discuss in this talk. So with this, I will finish my introduction, and let's talk about random stabilizer codes first. So this is a result in collaboration with Andrew Darmawan, Shiro Tamiya, and Hayata Yamasaki. And the paper is already on the archive. So if you are interested in the details, please visit and have a look. Good. So let me now focus on the random stabilizer codes and how to decode them efficiently. So in the second part of my talk, I would like to I would like to introduce random stabilizer codes and also our approach to decode these codes, which is based on the tensor network representation. And finally, we use this decoder for the checking the performance, quantum error correction performance of the random stabilizer code. Good. Okay, so what do we mean by random stabilizer code? So this is kind of related to Maria's question. So in random stabilizer code, we encode quantum information by using a random Clifford circuit. So assume that in the first place, we have lots of unsure qubits. So these zero states are just unsure qubits. And occasionally, we have logical degree of freedom, logical qubits. And let's say we have n physical qubits, and out of n, we have k logical qubits. So this is the initial setting. And we are going to encode these logical qubits by using a random Clifford circuit. So we just apply random Clifford gates to the pair of qubits. And mostly we assume that the connectivity of the circuit is one-dimensional, meaning that we apply Clifford gates to the nearest qubits. And we also assume that a random Clifford circuit has depth d. Okay, so this is a kind of parameter. And then this is the encoding operation for random stabilizer code. But of course, we are talking about stabilizers, so it's better not to talk about quantum state itself, but it's better to talk about stabilizers. So let me change the picture. So in the first place, instead of the state, we have trivial stabilizers. So ancillary systems, we have prepared the ancillary system to the computational zero state. So the stabilizer is, of course, Z operator, power Z operator, right? So we have Z operator here and there. And for the logical degree of freedom, we have just identity. So the trivial stabilizers are just G1, G2, and G3 we don't have because in this figure, I just put the logical degree of freedom, and G4, G5, and G6 is not there because it's a logical degree, and something like this. So in the first place, we have trivial stabilizers of n minus k. And then by applying the random Clifford circuit, each stabilizer grows to the random stabilizer. So we just sandwich these stabilizers by a random Clifford circuit, which is unitary, and we obtain a set of random stabilizers. And of course, this is a stabilizer group, so it defines a quantum error correcting code, and that is what we call a random stabilizer code. So a random stabilizer code depends on many things. For example, it depends on the depth of the circuit, and also it depends on the choice of random Clifford gates. But it turns out that the choice of random Clifford gates is not so important. So the actual parameter of a random stabilizer code is just the depth of the random Clifford circuit. Okay, so this is the code we are going to consider. Well, of course, we are not the first group who investigated random stabilizer code. And for in the last 10 years, people studied random stabilizer codes from different perspectives. So here I just wrote down the two main results. And one result obtained by Winton and Omar back in 2013, and they used the random Clifford circuit with all-to-all connectivity, and the depth is order log cubed of n. So all-to-all means the Clifford gate is applied to a pair of distant qubits as well. So it's really all-to-all connection in the circuit. And they proved that if we use this kind of random Clifford circuit, the code distance of the generated code is as large as the free random cores. So this is a kind of good because in terms of the code distance, at least, the generated code by this random Clifford circuit is as good as the free random cores. And a couple of years ago, 2021, Glantz et al. Also proved that if the random Clifford circuit is one-dimensional, the same setting as ours, and if the depth is log n, the generated code can correct the erasure noise very well. So they actually proved that this code is best code that can collect erasure noise. So this is also a strong result, and these two results already indicate that the 1D random Clifford circuit with log depth can generate a good code, maybe as good as a free random code. So this gives us a big motivation to study random stabilizer code. But the point is, in these studies, they don't talk about the complexity, I mean, decoding complexity. Because at least in the first result, this is about the code distance. So there is no concept about decoding in this study. And in the second result, they talk about erasure noise. So they, of course, use some decoding technique. But this is erasure noise. And in the erasure noise, we assume that we know the location of errors. So this is just an assumption of this noise model. And if we know the location of errors, it is pretty straightforward to decode any stabilizer code. And I would say decoding any stabilizer code against erasure noise is trivial because of this assumption where we know the location of errors. So in this study, they are not bothered about the decoding complexity. So the real question I want to ask is, can we efficiently decode the random stabilizer code when the noise is more realistic? So this is the question I wanted to clarify in this study. Okay, so let's go back to the setting of our study. So we have a random Clifford circuit to encode some quantum information, and we have some noise. We use independent depolarizing noise, which we believe to be a realistic noise, one of the realistic noise models. And then after the system becomes noisy by these depolarizing noise, we start the decoding process. And we want to argue the decoding complexity in this study. So this is a stabilizer code. So the first step of decoding is, of course, a syndrome measurement. So we have random stabilizer, and it becomes noisy after the depolarizing noise, but we just perform some syndrome measurement based on these random stabilizers. And we get error syndromes, plus or minus one sequence. And from these sequence, as usual, we are trying to guess what errors have happened on which qubits. So this is a decoding task, just general decoding task in the stabilizer code. And we are going to construct an efficient decoder for this to this end. And our approach is to use a tensor-network maximum likelihood decoder. And it turns out that this decoder is actually efficient in our case. Well, I'm not sure if you if you are familiar with the maximum likelihood decoder, but this is a standard decoder in stabilizer code, and it is known as a optimal decoder for stabilizer code. So this is a good side of maximum likelihood decoder, but also it has a big drawback that it is in general inefficient, extremely inefficient. So it takes exponentially long time to construct this maximum likelihood decoder. So in many cases, we don't actually use the maximum likelihood decoder because of this drawback. However, we found that in our case, by using a tensor network representation, maximum likelihood decoder can be efficient. So that is our kind of finding. So we use a tensor network representation to represent probabilities of possible logical errors. So if we know these probabilities, we can infer the most likely error. So computing probabilities is very important in this decoder. But by using the tensor network representation, we can efficiently do it. So here is a tensor. There are many strange tensors, but actually these tensors can be constructed from the outcomes of syndrome measurement. And what is important here is the size of this tensor. So the size of the tensor is n times order d. N is the number of physical qubits, and d is the depth of the circuit. And if we contract this tensor, we can actually compute the probability of possible logical errors. So contracting this tensor is a kind of time-consuming part in this decoder. But actually, the time cost for contracting this tensor is given by this scaling. So it is order n times d times 2 to the power of d. And if you look at this scaling, only possibly problematic part is this 2 to the power of d, right? But d is the depth of the circuit. So if the circuit has a depth, log depth, then this 2 to the power of d becomes polynomial of n, and the contraction can be done efficiently in polynomial time, right? So by using this tensor network representation, as far as the random Clifford circuit has a log depth, then we can actually construct an efficient decoder based on the maximum likelihood decoder things. Yeah, so this is a decoder we are going to use. So the whole picture of our numerical simulation is something like this. So we have a random Clifford circuit for encoding. We have noise and syndrome measurements. And based on the syndrome outcomes, we just use a tensor network maximum likelihood decoder, which is efficient if the depth is log n. And based on this decoding process, we can perform some error correction, and it's done. So this is the kind of the whole picture of our numerical simulation. And based on this, we can check the quantum error correction performance of the code generated by random Clifford circuit. And we did lots of numerics, but I will skip all of these and I just straightly go to the main result. That is this figure. So again, this is a kind of trade-off relation between encoding rate and the threshold depolarizing parameter. So this is exactly the same figure as those I have shown in the introduction. So the dashed line is the upper bound, and we have solid line, which is a hashing bound and achievable by free random calls. And these red points are the result we have obtained by using this construction of random stabilizer calls. As you can see, these points are almost the same as the hashing bound. So that means if we use a log depth random circuit, I mean random Clifford circuit, we can generate the code which is as good as a free random code. And of course, this circuit have many good properties. The encoding circuit is just 1D layout, and also the depth is just log n. And also on top of that, the coding task is efficient because of this log depth property of the random circuit. So we believe that this is kind of good class of quantum error correcting code because of these good properties. So to summarize the second part of my talk, we just considered the random stabilizer code, and our main message is that probably a good class of random calls is sitting in the intersection between stabilizer calls and random calls, and it has a very high performance. And the good properties such as high encoding rate, log depth encoding circuit, 1D layout, and also efficient decoding lead us to expect some practical applications of the code, of these code. So we kind of expect to have a real practical application of our proposal. But to this end, actually, we have to say one more thing. It's a future problem. So in this study, we assumed that the encoding circuit and syndrome measurement are noiseless. And of course, this assumption is very unrealistic. Everything is noisy in actual experiment. So to be really practical, we should consider noisy encoding circuit and noisy syndrome measurement. And if the quantum error correcting code works even for these noisy situations, maybe that's very good. And we could really use these random stabilizer codes in a real experiment. But yeah, this is a kind of future problem. And we are going to solve this problem in future. Okay, so yeah, this is
a
yep,
question that has
yeah.
come up is does tensor network with maximum likelihood achieve the upper bound?
Not necessarily. In our case, this upper bound you mean? No, no. In many sense. First of all, this is just an upper bound, and people strongly believe that this is not achievable. So it's just an upper bound. So the true line should be somewhere in between this dashed line and the solid line. So in that sense, probably we never achieve the upper bound. But at least in our case, the decoding ability of this tensor network is pretty good. So we also expect that we can use this tensor network technique to decode other class of stabilizer cores, but we have never done it.
Mhm. Yeah, great, thanks.
Yep. Okay, so thank you very much for the question. Yes, that is a good point to move on to the next topic. So in the rest of my talk, I will change topics and I would like to propose a new decoder based on the complementarity principle. Yes. So I will again start with our motivation about proposing a new decoder, and then I will show you the explicit construction. So we have been talking about random stabilizer code, but from now on, we just change our focus onto the random code, which is typically non-stabilizer code. And as I said, decoding is really non-trivial for this code because there is no syndrome measurement. So in this last part of my talk, I would like to explain how we can decode non-stabilizer random codes. But before that, maybe I should explain why I'm interested in non-stabilizer cores. Because in the second part of my talk, I just said random stabilizer cores can be efficient both in encoding and decoding. And also, they are as good as free random cores. So probably most of you think random stabilizer cores might be sufficient for quantum information processing. Yes, I agree with this. If you are interested only in quantum information processing, probably random stabilizer cores are sufficient, and we don't have to care about non-stabilizer cores. But I'm interested in non-stabilizer cores because they are interesting from the viewpoint of theoretical physics. In the introduction, as I said, there are many. There is a big interest in theoretical physics about quantum error correcting codes, and most cases, people care about non-stabilizer codes. For example, in the context of quantum gravity, people expect that the dynamics of quantum black holes for generate some random codes. And of course, the dynamics of the quantum black hole is different from Clifford circuit, for example. So in this study, they are interested in the random codes generated by dynamics of the quantum black hole, but that is definitely non-stabilizer random code. So this is one kind of motivation to talk about the non-stabilizer random codes. Well, I'm not an expert of quantum gravity, so I don't have many comments on that. Don't ask any question about quantum gravity. But on the other hand, recently I also found that quantum chaotic dynamics can be used as for generating random cores. So we just prepare quantum chaotic many-body system, and we have some Hamiltonian dynamics on the system. And actually, quantum chaotic dynamics is as random as free random, like hard random unitary. So we can actually use the dynamics of these things for generating a random code. And again, this random code is a non-stabilizer random code because again, this is not Clifford. So for these reasons, I'm interested in the non-stabilizer random codes. And personally, I find it exciting if we can achieve some quantum error correction experiment by using some dynamics in quantum many-body systems. So this is a kind of my ultimate goal to in the study of non-stabilizer random codes. And this is a motivation, at least to me. But if we are interested in quantum error correction experiment in many-body system, we should ask this question: how can we decode non-stabilizer random codes? So this is a question we want to ask, and we give one explicit construction of a decoder. Okay, so to answer this question, let me start with recording the how we usually decode stabilizer or CSS code. Maybe you can just generalize the way of decoding for stabilizer codes. So let me first remind of you how we decode CSS code. And in the case of CSS code, of course, we have some syndrome measurement. And from the syndrome outcomes, we collect logical power X and power Z and power X errors independently. So for instance, here we have a picture of the surface code. And to collect logical Z errors, we just perform some syndrome measurement. And based on this measurement outcomes, we just run classical decoder and we specify what we specify if logical Z error occurs or not. And we just correct it. And independently, we perform a different syndrome measurement to check logical X operators, right? And by combining these two decoding process for logical Z and logical X operators, it's done. We can construct a decoder for CSS code. So this is a general strategy of CSS code. So we can rephrase this strategy for decoding CSS code as follows. A decoder can be constructed from quantum measurements for logical power Z and X information. And here, quantum measurements are, of course, syndrome measurements in the case of CSS or stabilizer code. But our idea is maybe we can just generalize this idea. So maybe we can just construct a decoder from quantum measurements, even for non-stabilizer code. So that is our approach or idea to construct a general decoding. And it turns out that this is, in fact, the case. Even for non-stabilizer code, we can construct a decoder from two quantum measurements for logical power Z and X information. And this is the main result that I'm going to explain in the next few slides. But let me just explain step by step. So first of all, I want to clarify what I mean by decoding quantum and classical information. So decoding quantum information can be formulated in this way. So this is a very standard way to formulate the decoding task for quantum information. So in the first place, we prepare the maximally entangled state, and a part of the maximally entangled state goes to the encoding operation, and it becomes noisy. And after that, we perform some decoding operation. And if the final state between these two systems is close to the original maximally entangled state that we have prepared initially, then we say the decoding is achieved. So this is a kind of definition of decoding quantum information. And if the final state is close to the maximally entangled state, we have decoding error. So which we denote by delta Q of D. D is a decoding operation. Okay. So this is a kind of how we formulate decoding quantum information. On the other hand, when we talk about like classical information, such as logical power Z information or logical power X information, instead of preparing the maximally entangled state, we just prepare the basis state. So for example, when we talk about the logical power Z information, we first prepare the like 010 some computational basis state in the power Z basis. And this defines some bit sequence, right? And then we encode the information, classical information, and the quantum system becomes noisy. And finally, we try to decode what bit sequence we have prepared in the first place. But because we are interested in the bit sequence, instead of using the quantum channel or CPTP map, we can just use a POVM. So decoding is done by POVM when we are interested in the classical information. And if the outcome of the POVM is the same bit sequence as the initial one, we say we succeeded to decode the logical power Z information. And if they are close, we just say we have some decoding error, which we denote by delta classical Z, and MZ is a P of M used here. But of course, classical information can be dependent on the basis. So if we prepare the initial state in the Pauli X basis, we can define the logical Pauli X information. And we do the same thing. We perform the same encoding, and the quantum system becomes noisy. And after that, we perform some POVM measurement to decode the Pauli X, logical Pauli X information. Again, if we have the same string in the end, we say Pauli X information is correctly decoded. Okay, so these are the kind of formulation about decoding quantum and classical information. And if you think in this way, we have two POBMs to decode Pauli Z and Pauli X information. And also we have a decoder for quantum information. And the task we want to consider is we want to construct a quantum decoder from these two POBMs. So this is what we have done in this study, and I want to show you this construction explicitly. So this is kind of in parallel with the CSS code decoder, where POBMs are just given by syndrome measurement. So actually, this is just a generalization of the CSS decoder to the non-stabilizer code. And but in the case of non-stabilizer codes, there is no syndrome measurement, so we have to assume some POBMs that decode Pauli Z and X information. And from these, we are going to construct a quantum decoder. And how can we do this? So the first step is we use one POVM for decoding logical Z information to coherently extend it to the some quantum operation. So this is the first step. And by coherent extension of the POVM, we mean something like this. So here we have many different components. But first of all, VZ and the PJ, this is a Nymark extension of the POVM MZ. So Nymark extension is a very simple thing. So instead of performing the POVM onto the noisy quantum system, we just extend this noisy quantum system to a larger one, and we perform the projective measurement. And this is always possible for any POVM, and that is called the Nymark extension. So this BG is isometry that enlarge the quantum system, and then this PJ is a projective measurement. And after this Nymark extension, we perform this operation. So we have summation over J and PJ tensor JZ state. So this is we prepare some ancillary system, and if the measurement outcome is J, we coherently generate a JZ state, one of the computational basis state in the ancillary system. And of course, we don't measure. We actually, this is not a measurement. So we just prepare this, apply this operation. This is an isometry. So we just coherently, steal some information from the noisy system to the ancillary system. We just coherently copy it or make a correlation. And after that, we apply some quantum channel BZ inverse. And this is a kind of the quantum channel that mimics the inverse of this isometry. Well, of course, there's no inverse of the isometry, but we can mimic it by using some quantum channel. But this is a little bit technical thing. But this is the first step to construct a decoder from two POVMs. And if the decoding error for the classical Z information is 0, then we can prove that after this process, we have 3 quantum systems, and the state on these 3 systems is given by a noisy GHZ state. So it's something like this. So the first part corresponds to the top quantum system, and the second one is the middle one, and the third one is the bottom one. So as you can see, this is all IJ, IJ, and IJ, right? So this is really the GHZ state. And in the middle part, we apply, we have 2 quantum channels, right? But this is kind of essentially the GHZ state. So this is kind of good because the goal to construct a quantum decoder is we want to have a maximally entangled state in the end. But if we have this noisy quantum, noisy GHZ state, if we succeed to erase all the information in the middle part, so if we just erase this, we have a maximally entangled state, right? So the goal, the remaining task in this decoding is to erase all the information from the second quantum system here. And to this end, we can use the other P of M, MX. So we just measure the noisy system in by this P of MX. And depending on the measurement outcome alpha, we just apply some unitary correction to the ancillary system. And this second system is gone. And by using kind of, this measurement plays a role of quantum eraser. And then we can actually erase the second quantum system such that in the end of the day, we have a maximally entangled state if this error is zero. So this is the kind of, the way that we can transform two POVMs into the quantum undecoder. And for simplicity, I just assumed both errors for these POVMs are zero. But if they are not zero, we can prove that the decoding error for quantum information is bounded from above by essentially square root of the error for power Z and X classical information. So this is our main result. Yep. So we can actually construct, even for the non-stabilizer code, we can actually construct a decoder from two POVMs for decoding the power Z and X information. So this is the main message here. And we can show some properties of the decoder. And for example, this decoder is nearly optimal if the POVMs MZ and MX are optimal. And also we can demonstrate that by using the pretty good measurement for MZ and MX, the constructed decoder in this way can optimally decode the free random code against the erasure noise. So although the erasure noise is a kind of toy model, it's kind of good. We can explicitly demonstrate that we can decode free random code in this way. So we think this is a kind of nice result. So we have probably two lessons from this construction. A decoder for non-stabilizer code, as I said, can be obtained from POVMs for logical Z and X information. This is, again, in parallel with the CSS decoder, where these POVMs are just syndrome measurement. So in this case, it's kind of trivial that we can construct a decoder from quantum measurement. But the same strategy works also for the non-stabilizer code. And that is the main message in this study. And another lesson we can learn is the complexity of this decoder is nearly the same as the complexity of implementing the two POVMs, MZ and MX. So if we know the complexity of these POVMs, we can just translate it to the complexity of the decoder. And as I said, my ultimate goal is to understand the decoding complexity of non-stabilizer random codes. So we haven't succeeded yet, but we can address this question by addressing the complexity of POVMs for decoding power Z and X classical information for non-stabilizer random codes. So in near future, maybe I hope I can say something about the decoding complexity for this. Okay, so that's pretty much everything I have prepared. So let me summarize my talk. So in this talk, we are concerned with the decoding complexity of quantum random code. And in the first result, we talked about the random stabilizer code generated by 1D random Clifford circuit. And we said that we proved that both encoding and decoding operations are efficient in this case, and the quantum error correction performance is also as good as the free random code. So we have to think about the noisy circuit and noisy syndrome measurement, but I hope in the end of the day, we can use this random stabilizer code in practice. And in the second part, we talked about random non-stabilizer code, and we showed that we can construct a decoder for these code from two POVMs. And we haven't finished this research program yet, But in future, I hope I can say something about decoding complexity for non-stabilizer random calls. My dream is to say like quantum error correction by chaos or something, but it's still far away. But anyway, yeah, I will finish my talk here. So thank you very much for your attention.
Thank you. Thanks for the talk, Yoshifumi. That was really interesting and yeah, really nice presentation as well. And cool to see, yeah, all these different ways of thinking about decoding random codes. We have time for one question. We have a question that came in: is the fidelity of qubits assumed by random code the same as for stabilizers for QEC? And do we need physical full 2D grid connectivity of qubits for implementing a 1D random code for quantum error correction?
So in the first part, first of all, the connectivity. I mean, the second question is about the connectivity, right?
Yeah.
It's definitely just 1D. So it's just like we just apply the Clifford gates to the nearest gate, nearest qubits, and the qubits are aligned on the line. So it's really 1D. But on the other hand, if we can also consider the random circuit with 2D layout, and in that case, this depth can be shorter. So if we increase the connectivity, the depth becomes shallower and shallower. So there's an advantage. So it's a kind of trade-off between the performance and experimental difficulty. And sorry, what was the first question? Can you say it again? Fidelity?
Yeah, the first question was, is the fidelity of qubits assumed by random code to be the same as for stabilizers for quantum error correction?
Yes. Yes. So in the second part, yeah, here I just propose some decoder, but this is rather theoretical result in the sense that we assumed everything noiseless. So fidelity should be 1 in this study. So it's pretty much a future work to consider like noisy quantum state, noisy qubits in this case.
Great, thanks. And yeah, we're going to have to wrap up there, but thank you very much for the talk, Yoshifumi, and thank you everyone for joining us and for all the questions. It's great to interact live, and yeah, very soon we have the Qiskit Global Summer School closing ceremony, which will be streamed on YouTube at 6:30. Well, for me, 6:30, or whatever time it is for you. And so please, yeah, tune in and join us next week. And we have lots of thank yous coming in the comments for the talk. So yeah, thanks, Yoshifumi. Do you have any final words for our audience before we finish?
Well, yeah, thank you very much, everyone, for coming. And it was a great experience. And I hope you enjoyed my talk. So I wish you have a nice day.
Great, thanks. Bye, everyone.